What if I told you that the secret to maximizing power efficiency and reliability of your power system could lie in a simple technique? A technique so influential that it can keep your power system up and running even when parts of it fail, and yet so adaptable that it lets you fine-tune response to changing power demands. Would you be intrigued? Well, that's precisely the magic of the parallel operation of transformers. Now you might be wondering, why is it more economical to install numbers of smaller rated transformers in parallel than installing a bigger rated electrical power transformers? Well, this has mainly the following advantages. Efficiency. Transformers are most efficient at full load. By using parallel transformers, you can only run what's needed, keeping them closer to full load for better efficiency. Availability. If one transformer needs maintenance, the others can handle the load, minimizing downtime. Reliability. If a transformer, remaining ones can share the load, potentially preventing a complete power outage. Flexibility. Adding or removing transformers in parallel allows you to easily adjust to changing power demands. This avoids the unnecessary expense of a giant transformer for future needs or inefficient operation with a large transformer for a smaller current load. But why exactly is the parallel operation so beneficial? And how does it offer such astonishing advantages? Let's unravel this fascinating mystery and also explore the conditions necessary for these parallel operations to work effectively. Imagine two or more transformers running in parallel. For optimal performance, they need to satisfy several key conditions. They must have the same voltage ratio, the same percentage impedance, the same polarity, and the same phase sequence. Let's dive into each of these conditions in greater detail. First up, the voltage ratio. Simply put, if two transformers with different voltage ratios are connected in parallel to the same primary supply voltage, their secondary voltages will differ. If these secondaries are connected to the same bus, a circulating current will flow between them and consequently between the primaries. Since transformers have a small internal impedance, even a slight voltage difference can cause a high circulating current, leading to unnecessary extra Y2R loss. Next, we have the percentage impedance. The current shared by two parallel running transformers should be proportional to their MVA ratings. Simultaneously, the current carried by these transformers is inversely proportional to their internal impedance. This means that the impedance of parallel running transformers should be inversely proportional to their MVA ratings. In other words, the percentage or per unit impedance values should be the same for all parallel running transformers. I've also made a detailed video on percentage impedance. I recommend watching it for a better understanding. The link is in the description. Then we have polarity. All transformers operating in parallel should have the same polarity, or the instantaneous direction of induced EMF in the secondary. If two transformers have opposite instantaneous directions of induced secondary EMF when fed the same input power, they are said to have opposite polarity. If the directions are the same, they have the same polarity. If the polarities are not the same, a huge circulating current will flow in the transformers, but no load will be fed from them. Finally, there's the phase sequence. This refers to the order in which the phases reach their maximum positive voltage. For two parallel transformers, this sequence must be identical. Otherwise, each pair of phases will be short-circuited during the cycle. These conditions are critical for the parallel operation of transformers. However, achieving identical percentage impedance in two different transformers can be challenging in practice. That's why transformers running in parallel may not have exactly the same percentage impedance, but their values should be as close as possible. To sum up, for transformers to operate efficiently in parallel, they must have the same voltage ratio, percentage impedance, polarity, and phase sequence. By adhering to these conditions, power systems can avoid unnecessary losses and operate at their maximum efficiency. So, the next time you see transformers humming away, remember the precise conditions they need to meet to work together in harmony. That's it for today's topic on mastering the art of parallel transformer operation. If you found this video helpful, don't forget to hit the like button and share it with your friends and colleagues. And if you haven't already, do subscribe to our channel for more electrical engineering related topics. We would love to hear from you, so if you have any queries or topics you'd like us to cover, make sure to drop a comment below. Stay tuned for more interesting topics. Until then, keep exploring and keep learning. Your journey to mastering electrical engineering continues here with us. See you in the next video.